Okay, so having done the four boundary conditions, that is what is happening to the electric and the magnetic field vectors as they cross the boundary between medium 1 and medium 2, we're now ready to get the Fresnel equations underway. And I start by drawing a diagram which should be pretty familiar to everyone. Here is my surface once again between my medium 1 and my medium 2. And I'm going to shine in. This is now the direction of the actual light, if you like. This is the incident beam. There will be a reflected beam. And there will be a refracted beam. Now the problem with the refracted beam is that also starts with the letter R, and we'll get confused. So I'm going to call the refracted beam the transmitted beam. The angle of incidence is angle I, the angle of reflection is angle R, and the angle of refraction or transmission is the angle T. And of course we know that the angle of incidence is equal to the angle of reflection, but not the angle of refraction. That is a fairly standard light ray diagram. These are the incident beams, reflected beams, and transmitted or refracted beams. Now let's just think for a moment about the electric field associated with this beam of light. So the light is travelling in this direction. The light is travelling in this direction. So where is the E field? The answer is, and I've got a match here, and I'm going to make that match the E vector. And the fact is that E vector can be anywhere on a plane that is perpendicular to the direction of travel. It cannot be in that direction because that is then not perpendicular to the direction of travel. It must always be somewhere in a plane. If I put my hand there, if you can see, my hand is a plane perpendicular to the direction of travel. So the E vector must sit somewhere on that plane. It cannot be anywhere else because it must be perpendicular to the direction of travel. And that, of course, is also true for the reflected and the transmitted or refracted beams. It must be somewhere there. We don't know where it is, and indeed, if this is unpolarized light, then the E vectors will be in all directions. But whatever directions they are, we can resolve them into two component parts. One component is what I call the perpendicular component. That is the component that is sticking out of the paper. The other component is 90 degrees to that. That is the component that is parallel to the paper. So all E fields can be resolved into this one, the parallel one, and this one, the perpendicular one. So I'm just going to completely redraw this diagram twice so that we can use it once for the perpendicular version and once for the parallel version. So there are my two diagrams. They're identical to the one I drew before. You've got an incident beam, a reflected beam, a refracted beam. And now we are going to consider the two circumstances that we had before. One will be the perpendicular E component and one will be the parallel component. Remember, we said that the perpendicular component comes out of the paper, the parallel component lies flat on the paper or is parallel to the paper. So we can draw this is the perpendicular one, which we will draw with a dot. The dot simply means that the E field is coming out of the paper straight at you. That's the component of the E field in the perpendicular direction. On this diagram, we're going to draw the E field, which will be parallel to the paper, and it will look like that in each case. In each case, it is, of course, perpendicular to the direction of travel and sits on the plane of the paper because we've resolved the E fields into the two constituent parts. Now let's just think about the B fields associated with each of those perpendicular and parallel E fields. Well, the B field for the perpendicular E field will be parallel to and in the plane of the paper. So that's the B field, this is the B field, and that is the B field. And in each case, we can resolve that B field into its vertical and horizontal components. There is the horizontal component, there's the vertical. Over here we've got a horizontal component and a vertical. And here, although it won't be very clear, we've got a horizontal component and a vertical component. When we move over to this direction, the B field, of course, if the E field is parallel with the paper, the B field must now be perpendicular to the paper. So the B field is either coming in or going out of the paper. We'll ignore that for the time being. What we do know is that we can resolve the E fields, and I've just noticed that I've drawn that the wrong way round. That should be in there because it's always on the left when you go, when it's reflected it will still be on the left. So this is the E field parallel to the direction of travel, and once again we can resolve E fields into vertical and horizontal components. Alright, so essentially we are simply resolving those components which are in the plane of the paper. Now let's just do a little bit of geometry. We will take the incident beam. That is the angle of incidence. Here is, let us say we're taking this diagram here, so we're looking at the B field. So here is the B field, which of course is at right angles with the direction of travel of the beam, and just to labour the point, the E field is perpendicular, sticking out of the page, but we'll ignore that for the moment. And what we have said is that we can resolve this B field, let's make it a bit bigger so we can see what we're doing. We'll resolve that B field into two terms. We've got a vertical term and a horizontal term. That is just simply resolving this B field in its two component parts. Now if this angle here is the angle of incidence I, then that angle there will also be the angle of incidence I, and that angle there is also the angle of incidence I. And that tells us that the horizontal component of the B field will be B cosine of I, and the vertical component of the B field will be B times the sine of I. That's just resolving the component parts. And that is going to be true for the reflected waves and for the transmitted or refracted waves, except the angles are now going to be the angle R for reflection or T for transmission. Now, although we defined 4 boundary conditions, we're actually only going to need 2. And that are that E1H equals E2H and B1H equals B2H. That is to say, the horizontal components of the E field transport across the boundary, and the horizontal components of the B field transport across the boundary. So any component of the electric or magnetic field which is parallel to the boundary or horizontal to the boundary is going to transport across it. Let's therefore look at the left-hand diagram up here. This is the E perpendicular. That means the E field is sticking out of the paper. That E field, I hope you will agree with me, is parallel to the boundary because of course the boundary is sticking up at us out of the paper. And so that E field is actually parallel to that boundary. It's sticking out of the paper and so is the surface. So the E field is parallel to the boundary. And if that's the case, then the E fields must transport across that boundary. And that means that the total E field in medium number 1, which is the incident E field plus the reflected E field, must equal the transmitted E field, because the E fields transport across the boundary. So that gives us that the incident E field plus the reflected E field, which are the two E fields in medium number 1, must equal the transmitted E field, which is the only E field in medium number 2. But we can also look in diagram number 1 at the horizontal B fields. They are also parallel to this boundary, so they will also transmit across. Now, what are they? Well, we've got the incident B field. Don't forget we established that the horizontal component is the B field times the cosine of the angle. So this will be BI, the incident B field, times the cosine of the angle I. Then you will have to take minus the reflected B field because it's in the opposite direction. This is going in that direction, this is going in this direction. So we've now got to have minus BR, the reflected B field, times the cosine of the reflected angle is going to be equal to, well, in this case it's the same direction as the incident B field, so that's going to be equal to BT, the transmitted or refracted B field, times the cosine of the angle of refraction. Just a reminder that these two equations here were derived as a result of these boundary conditions. The horizontal or the parallel components to the surface transport across. So the total E fields, the total horizontal E fields and the total horizontal magnetic fields are the same. That's why we got those two terms. Now we can just remind ourselves of something we learned in the video on what is light, that B, the magnitude of the B vector, is equal to the magnitude of the E vector divided by the speed of light. But that is for vacuum. For a dielectric media, it will be E divided by the speed of light in that media, and the speed of light in a media is equal to the speed of light in a vacuum divided by the refractive index. So this just becomes N over C, the speed of light in vacuum, times E. So now I'm going to substitute for B in this equation. For B, I'm going to substitute N over C times E. So consequently, I'm going to get, since we are in medium 1, I'm going to get that N1 over C times EI, because it was BI, so it's going to be the associated EI, times the cosine of the angle of incidence, minus, now I'm still in medium 1, so it's going to be N1 over C times now ER, because it's the associated reflected field, times the cosine of R, is equal to, now we're in medium 2, so it's N2 over C times the respective E field, ET, times the cosine of T. And you can see that the C's will simply cancel out throughout. So now I'm going to rewrite that equation so that you can see it. So there it is again, N1 EI cos I minus N1 ER cos R equals N2 ET cos T. Now we just need to remember a few things. The first is that the angle of incidence is equal to the angle of reflection, and I'm going to call that theta 1. The angle of transmission, or the angle of refraction, I'm going to call theta 2. And I'm just going to remind you that we showed that EI plus ER equals ET for the perpendicular vector. So now I'm going to rewrite this equation, except that for angles I and R I'm going to put theta 1, and for angle T I'm going to put theta 2. And when we get to ET, I'm going to substitute EI plus ER. So here goes. That will give me N1 EI cosine theta 1, or theta 1 because that's I, minus N1 ER cosine theta 1, because that's cosine R, is equal to N2 ET. Well, ET is EI plus ER times the cosine of T, but T is theta 2. And I've just slightly adjusted the camera so that cosine theta 2 comes on. Now here's the trick. What we want to do is to rearrange this equation so that we get all the EI terms on this side of the equation and all the ER terms on that side of the equation. So let's do it. Well, here's an EI term, that's N1 cos theta 1, or theta 1. And here's another EI term, that's N2 cos theta 2, but when you bring it on the other side, that will become a minus N2 cosine theta 2. And that equals the ER terms. Well, on this side we've got N2 cos theta 2. And on this side we've got a minus N1 cos theta 1, but when you bring that on the other side it becomes a plus N1 cos theta 1. And now we can say that ER divided by EI is equal to, so this term divided by this term will be this in brackets divided by this in brackets. And I've overshot again, I realise that, but it will become clear, I hope, that that is equal to N1. Remember, it's this term here, which is N1 cos theta 1 minus N2 cos theta 2, that's this term, divided by this term, which is, I'll just reverse these two, so you've got N1 cos theta 1, because there's a cos theta 1 sticking there that you may not be able to see, plus N2 cos theta 2. You don't need that bracket there. And that, you'll be pleased to know, is the first Fresnel equation. And what does it do? It tells us that as far as the perpendicular vector of E was concerned, because we've only been dealing with the perpendicular vector, the ratio of the reflected component of the E term to the incident component is given by this term here. So if you want to know what is the proportion of the E field that is reflected compared with that which is incident, Fresnel's first equation tells you that. But it's in respect of the E field that was perpendicular. We haven't yet done the E field that was parallel. That is still awaiting us. Well, now we can get to the second Fresnel equation fairly easily by simply looking at this formula here. And we can now say that ER is equal to ET minus EI. That just comes straight from this, ER is ET minus EI, just comes straight from this formula here. So now we're going back up to the formula at the top. And once again, we're going to substitute theta 1 and theta 2 for I and R and T. But this time, we're going to change ER into ET minus EI. So unfortunately you can't see it, but I hope that you'll be able to remember, well, you probably won't be able to remember, but I'll tell you that the formula therefore becomes N1 times EI times the cosine of theta 1 minus N1 into ER, but for ER we're going to put ET minus EI times the cosine of theta 1, or theta 1, is equal to N2 times ET times the cosine of theta 2. And again, the trick is to bring all the EIs to one side and all the ERs to the other. So here we've got an N1 cos theta 1 for an EI term, and then we've got a minus minus, which is a plus N1 cos theta 1, And now we want the ER terms, sorry, the ET terms, because we have substituted for R, so we've got ET on this side of the equation. And here we've got an N2 cos theta 2, that's that term. And over here we've got a minus N1 cos theta 1, but that will become a plus when we go on the other side. So plus N1 cos theta 1. And then as we did before, we can take ET divided by EI, and that will be this term divided by that term. Well, this is N1 cos theta 1 plus N1 cos theta 1. Well, that's just 2 times N1 cosine theta or theta 1 divided by this term here, which to tidy up we'll just bring it round the other way. That becomes N1 cos theta 1 plus N2 cos theta 2. And that is Fresnel's second equation. We must remember that it relates to the perpendicular value of E. It's the second Fresnel equation, and it relates the transmitted or refracted electric field to the incident electric field. Now, all of that, you will remember, was for the perpendicular E field. That was the diagram on the left-hand side. Now we have to go to the diagram on the right-hand side, which I'm going to redraw. So there it is. That's exactly the same diagram as on the right-hand side. This is where the B vectors are now sticking out of the paper, and the E vectors are parallel to the paper. The E vector is always at right angles to the direction of travel of the wave, and we have resolved each of the E vectors into a vertical and horizontal component. And just as before, we can say that the horizontal component will be the respective E vector times the cosine of the angle, in this case of incidence, but it could be of reflection or transmission. And the vertical component is E times the sine of that angle. And I just remind you again of the boundary conditions that are relevant here, that the EH1 equals EH2 and BH1 equals BH2. That is to say, the value of the total electric field that is parallel to or horizontal to the surface in medium 1 will equal the E field in medium 2, the horizontal one, and the horizontal magnetic field in medium 1 will equal the horizontal magnetic field in medium 2. Those are the two key boundary conditions which we've derived and which we need to use. So remember, in this case it is the magnetic field which is sticking up out of the paper. And if the magnetic field is sticking out of the paper, it is parallel to the surface, because the surface also sticks out of the paper. So consequently, we know that because the parallel fields transport, the total B field in medium 1, which is BI plus BR, is going to equal the total magnetic field in medium 2, which is BT. We can also say that the parallel E fields in the diagram which I drew will also transport across. So the incident parallel E field will be EI, and then the parallel one, or the horizontal one, you remember, uses the cos term, cosine I, minus ER, because it's in the other direction, of cosine R, equals ET of cosine T. That's the same principle that we used earlier when we were looking at the perpendicular E field, but now, of course, we're looking at the parallel E field. It's the E field that's parallel to the paper. And once again, we remind ourselves that B is equal to N over C times E. And I'm going to substitute for B N over C times E in this formula here. So I'm going to get, since we're in medium 1, I'm going to get N1 over C times EI. That's this term here. Plus, we're still in medium 1, so it's N1 over C times ER equals once we get into the refracted wave, we're in medium 2, so that's now going to be N2 over C times ET. The C's, of course, just cancel, so that's no problem. And if you rearrange this formula by dividing through by N2, you should be able to see that ET is equal to N1 over N2 times EI plus ER. All I've done is to divide by N2, so you've got N1 over N2, N1 over N2, both of those can come outside into EI plus ER. And now we substitute for ET in this formula, this here. So we're going to get that EI, start well over on the left hand side, EI times cosine I minus ER times the cosine R equals, that's this formula up here, down a bit so you can see it. So far no change, but for ET we're going to put in this here, N1 over N2 into EI plus ER times cosine T. Now, I'm going to do two things. Firstly, I'm going to multiply through by N2. And secondly, for I and R, I'm going to put theta 1, and for T, I'm going to put theta 2. So if I can remember how to do all of that lot, that should come out to N2 times EI times the cosine of theta 1 minus N2 times ER times the cosine of theta 1, because incidence and reflection are the same, is equal to N1, because we've multiplied by N2, so that goes, into EI cosine theta 2, because T is now theta 2, plus N1 ER. I've just panned out a very tiny amount so that we can get cosine theta 2 in here. That's cosine T becomes cosine theta 2. And now it's the same trick as before. You want all the EI terms on one side of the equation and all the ER terms on the other side of the equation. And I hope I can fit them all in. So what are the EI terms? Well, we've got one here, N2 times cosine of theta 1. N2 cosine theta 1. I've got another EI term here, which is N1 cos theta 2. When you bring that across, that must be minus, so minus N1 cosine of theta 2. What about the ER terms? Well, on this side, I've got an N1 cos theta 2. And on this side, I've got a minus N2 cos theta 1, which when you bring it over to the other side will become a plus N2 cosine theta 1. And now I can do what I did before. ER over EI is equal to this term divided by this term. And this term is going to be N2 cos theta 1 minus N1 cos theta 2 divided by this term, which is N1 cos theta 2 plus N2 cosine theta 1. And that is the third Fresnel equation. And that relates, remember, to the, make it clear, the parallel E vector. We did the perpendicular before, we're now doing the parallel in the plane of the paper. And that relates the parallel reflected E vector to the parallel incident E vector. Just one more Fresnel equation to go. If we look at this equation here, divide by N1 and rearrange, we will get that N1 ER equals N2 ET minus N1 EI. And that means we can get an equation for ER, which is equal to n2 over n1 et by dividing by n1. And now n1 divided by n1 is just 1, so that's minus ei. Now I'm going to substitute for er in this equation here. Unfortunately, we can't see them both on the screen at the same time, but what that will give you is that ei cosine I minus, and now instead of er, we're going to have this term here, so it's minus n2 over n1 et minus ei, that's all er, times the cosine of r, equals et times the cosine of t. So in the next line, what we're going to do is to multiply through by n1 and change I and r to theta 1 and t to theta 2. So let's see if we can get that right. We're multiplying through, so we're going to get that ei n1 times cos theta 1 equals, minus n2 et times cos theta 1, minus times minus is plus n2, that's right, times ei cosine theta 1 equals et, well, we're multiplying through by n1, so it's n1 et cos theta 2. And once again, the trick is to bring all the ei's to one side and to bring all the et's to the other side. So what have we got? For ei, I've got an n1 cos theta 1, and I've got a plus n2 cos theta 1. Sorry, I've just spotted an error. When we multiplied by n1 throughout in this equation to get this equation, I should have multiplied ei by n1, not by n2. So that should be n1 and that should be n1. I will have already put up an annotation to alert you to that earlier, but I've only just spotted it myself. That's a mistake. That should be n1. That should be n1 because what we did with this equation is we multiplied through by n1, and that means that ei gets multiplied by n1. That's my dog barking outside, but you've already met her. So that's the left-hand side. Now what about the right-hand side? Well, we've got an n1 cos theta 2 on that side. And here we've got a minus n2 cos theta 1, which when we take it over the other side will be a plus n2 cos theta 1. And now we can do the et divided by ei, and that's going to be this term divided by that term. So this term is n1 cos theta 1 plus n1 cos theta 1, so that's simply 2 n1 cos theta 1 divided by this term, which is n1 cos theta 2 plus n2 cos theta 1. And that is Fresnel's fourth equation for the parallel E vectors, and that tells you that for the parallel E vector, the ratio of the transmitted E vector or the refracted E vector to the incident E vector is given by this equation. So there they are, the four Fresnel equations. Well, at the moment there's only three. If I scroll up, those are the four Fresnel equations that we have just derived, which for the perpendicular and parallel components of the E vector reveal in each case the reflected E vector compared with the incident E vector and the transmitted E vector compared with the incident E vector. And let's just consider one consequence of Fresnel equations. What happens when theta is 0? If theta 1 is 0, theta 2 is 0. What we're talking about then is, quite simply, here is the surface, here is the electromagnetic radiation coming in at 0 degrees, in other words perpendicular. So the incident radiation comes in, some of it is reflected and some of it is transmitted. And what Fresnel enables you to work out is how much. Because as far as the ER divided by EI term is concerned, if you look up here, don't forget cos 0, because theta is 0, cos 0 will be 1, so this just becomes n1 minus n2 divided by n1 plus n2. So this is equal to n1 minus n2 divided by n1 plus n2. What about the transmitted? Well, that's going to be 2n1, because this is 1, divided by n1 plus n2. So ET divided by EI is going to be 2n1 divided by n1 plus n2. Now let's consider we're going from air to glass. N1, which is for air, well that's 1, and N2 for glass is 1.5. Consequently, the reflected compared to the incident vector is going to be N1 minus N2, which is minus 0.5, divided by N1 plus N2, which is 2.5, which is equal to minus 0.2. The minus sign simply indicates that there's a phase shift. The transmitted vector compared to the incident vector is going to be 2n1 divided by n1 plus n2. Well, 2n1 is 2, n1 plus n2 is 2.5, and that's 0.8. But those are the E vectors. You'll remember that with the pointing vector we showed that the intensity of the radiation is proportional to E squared. So if we want the intensity of the reflected wave compared to the intensity of the incident wave, we're going to need the R over I term here squared. And minus 0.2 squared is 0.04, which is 4%. So what we've shown is that when light coming from air to glass is incident at 0 degrees, 4% of it is reflected. 96% of it goes through, and that's presumably why we use glass for windows. It means most of the light is transmitted through the window, very little of it is reflected. The same would also work, of course, for water, but water is very difficult to keep in window frames. And now, as a special reward for all of you who have laboured through the development of these Fresnel equations, you will know that sometimes my videos are interrupted by my clock, and some people have asked to see it. So here to finish the video, and as a special reward for your attention, is my clock, showing why it makes the sound it does.